Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2024 paper of Chemistry Unit 4. Moving on to question 1, we are given this reaction below. In part A, we are asked that we are told that some collisions between reactant molecules do not lead to the formation. We have to figure out which is the best explanation for this. Less collisions are leading to formation. So we are told that some of the collisions do not lead to the formation of products. If the concentrations are low, so the first option, if concentrations are low, number of collisions will decrease, but the proportion of successful collisions will not. So B will be the answer over here, because if the collisions have less than the energy that it's needed, so less than sufficient energy, they'll collide, but they won't have enough energy to form the products. In option C, we're told that the reaction is at equilibrium. If that happens, the forward and backward reaction will be occurring at the same rate. The proportion of successful collisions will not change, and same for part D. Now in question B, we are asked what's the coefficient of the equilibrium constant Kp. Kp over here will be d to the power 4 divided by pressure, so partial pressure of d to the power 4 partial pressure of A times the partial pressure of B squared. This we won't consider C because it's a solid, so it won't have a pressure. So if we find the unit, we have atmosphere to the power 4 on the top, we have atmosphere for A and atmosphere square for B, so atm to the power 4 divided by atm to the power 3, so we'll get atm. A is our answer. Now in question 2, nitrogen 5 oxide in 2O5 decomposes in a first order reaction at 45 degrees Celsius. The half-life is 1400 seconds. We are told that the initial concentration is 1 mole per dm cube. We have to find the concentration after 4200 seconds. So 4200 divided by 1400 would be 3. So 3 half-lives. The initial concentration is 1. After 3 half-lives, the concentration would be 1 into half cube, which would be 0.125. D is our answer. Now in question 3, we are told that ammonia is produced by the reaction of nitrogen with hydrogen in the presence of an iron catalyst. We have to find which of the following statements about the catalyst is not correct. Catalyst lowers the activation energy, that's right. Catalysts also have no effect on the equilibrium constant, because the equilibrium constant, so Kc, will depend on the concentration of H3 squared divided by the equilibrium. The catalyst does not affect the equilibrium position, as it increases the rate of the forward and backward reaction in the same proportion. In option C, it states that it alters the enthalpy change. This is wrong, so C is our answer. If we see a energy level diagram, this is an exothermic reaction, so So this is the enthalpy change. And somewhere over here is the activation energy. So this level is the activation energy. And this is how it happens. So basically there is an intermediate state over here. So we go there and then come down here. This is the activation energy in this case. With the catalyst, this level comes down, we get an alternative route. So this is our new activation energy, which is less than before. However, the enthalpy change, the gap between this, so this gap stays the same. So the addition of a catalyst does not change that. Option D is also right. Catalysts reduce the energy cost because we don't have to maintain the same high temperature and pressure if we can use a catalyst instead. Now we are told that which condition favors the highest percentage of ammonia in the equilibrium from identical amounts of nitrogen and hydrogen. Since this is an exothermic reaction, a lower temperature will promote the forward reaction. So lower temperature promotes or shifts the equilibrium to the right. And if you think about pressure, there are 4 moles of gas on the left and 2 moles of gas on the right. So if we increase the pressure, the forward reaction will be favored. So if pressure is increased, equilibrium shifts to the right. To get a higher proportion of ammonia, we'll need a higher pressure and lower temperature. So 400 degrees Celsius is basically 673 kelvins. So this is a higher temperature than 400 Kelvin. So we will find an answer in A and B. C and D are out. Now if you think about the pressure, now 1 atmosphere is around 100 kilopascals. So this is a bigger value. So this value is around 200 into 100 kilopascal. So this pressure is greater than this pressure. So this is the higher pressure and the lower temperature. So option B is our answer over here. Now in question 4, we are given 3 reactions involving hydrogen. We have to order this in increasing standard entropy change, so del S system. Here we'll consider the change in gaseous moles. So on the left we have 4 gaseous moles, on the right we have 2. In this case we go from 3 to 0, and on this one we go from 1 to 2. So the place where there is a bigger change in this, a bigger increase would mean a more positive del S system. A decrease would mean negative del S system. The more negative this change is, the more negative the del S system. Since K also converts this into a liquid, the del S system will be most negative for K. So K would be our first term. So A and D are out of our option. Now between B and C, J will have the second lowest del S system because it has a decrease in gaseous moles. So option C will be our correct answer. L has an increase in gaseous moles, so we'll have a positive del S system for that. Now in question 5, we're told that methane reacts with steam to produce carbon dioxide and hydrogen. We are given the molar entropies for the reactants and products. We have to find the del S system. So in this case, del S system so we'll have the standard entropies of the product, which is 214 plus 4 into 131 minus for the reactants we have 186 plus 2 into 189, so we'll have 738 minus 564. This will be plus 174. So option D is our answer. Now we have to find what are the signs of entropy change at 373 Kelvin when water vapor condenses. This is condensation over here. We're going from water to liquid gas or liquid water. So we're going from steam to water. So this is steam, this is water. When we go from steam to water, so when condensation happens, del H will be negative. So basically this is an exothermic reaction. So condensation is exothermic. Del S surroundings is minus del H by T. Since del H is already negative, minus del H will be positive, so del S surrounding will be positive. So option B and D are out. Also, since we are going from a gas to a liquid, the del S system will be negative because in the disorder in gas is more than that in liquid, so that decreases. So C will be our answer. Now we're told that at 50 degrees Celsius the ionic product of water is over here. Since this is not room temperature, the pH of water will not be 7. And since we are told that this is water, we didn't add anything, it must be neutral. So B is our answer. At any temperature, water would be neutral, but if we increase the temperature, the pH with an increase in temperature, the pH value will decrease, but so will the pH scale will also change. So for this temperature, if we have the pH scale, 6.6 in this would be the neutral value. If we go less than 6.6 here, we'll get acidic, and if we go to the right, we'll get alkali. If we increase the temperature more, so at 100 degrees Celsius, it would be around 6, so 6 would be the neutral value. On the left we'll have acidic, on the right we'll have alkaline. So no matter the change in pH, water will always be neutral, so it must be between these two. We are not getting alkaline or acidic water just because the temperature changes, and since we are increasing the temperature, the pH value will decrease, so it won't be 7 anymore, it will be 6.6. Now we are told that equimolar solutions of 4 acids are prepared. which solution has the lowest pH value. The change between this molecule is the third hydrogen being replaced with one of the halogens. So if we draw the structure, we'll have CH2, we have a carboxylic acid over here, and this is our variable one. So first we put hydrogen over here, then chlorine, then bromine, then iodine. In between these four, chlorine is the most electronegative, so this will cause this hydrogen, the electropositivity of this hydrogen will be the greatest if chlorine is over here. If chlorine is over here, it's the most electronegative among all of them. This will the chlorine wants electron, so it will pull the electron from here onto its, so it will pull the electron towards itself. So the electronegativity of this oxygen will increase and the electropositivity of this hydrogen will increase. So the chlorine, since it pulls the electron from here, it reduces the electron density over here. If the electron density near the hydrogen is lower, it will be a stronger acid, so it will have a lower value of pH. So P is our answer. Now we are given some equation of acid-base equilibria. We have to find the conjugate acid of HPO4 minus. The conjugate acid of HPO4 would have one more hydrogen than that. So H2PO4 minus will be our answer. H3PO4 is the conjugate acid of H2PO4 minus. H2PO4 minus is the conjugate acid of HPO4 minus, and HPO4 minus is the conjugate acid of PO4 minus. Now in question 10 we are asked the pH of 0.2 mole per dm cube solution of strontium hydroxide. We are given the value of Kw. Since this is an hydroxide, we'll find the pOH value and then use that to find the pH value by subtracting it from the pKa value. So pH is pKa minus pOH. The pOH value for strontium hydroxide would be minus log base 10 the concentration of OH. The concentration of OH would be 0.200 times 2, since there are 2 hydroxide per each mole of strontium hydroxide. If we calculate this, we'll get a value of 0.398. So the pH would be the pKa, which is minus log 1 into 10 to the power minus 14. This will come out to be 14 minus the pOH, which is 0.398. We'll get a value of 13.6. So B is our answer. In question 11, we are told that carbon is an oil used in aromatherapy. We have in question A, we have to tell if it shows geometric and optical isomerism, only geometric isomerism, optical isomerism, or neither of them. If we search for a chiral center for the optical isomer, we have this is a chiral center. Since we have this group on one side of it and this group on another, this group on another, and a hydrogen. So there are 4 different groups of groups. So any point with 4 different groups of atom bonded to it is a chiral center. This is a chiral center, so optical isomerism will be shown here. For geometric isomerism, we need restricted rotation and 2 different groups around. So a double bond or a triple bond is somewhere where restricted rotation happens. So in this case, geometric isomerism will not be shown because there are 2 identical groups of atoms on the carbon. However, if we have chlorine over here, we have chlorine and hydrogen. This will show a geometric isomerism with the chlorine and hydrogen flipped. So this is a Z isomer, this is the Z isomer, and this is the E isomer. In this case, we have restricted rotation over here, since this is a cyclic compound. In cyclic compounds, we don't necessarily need double bonds to have restricted rotation. It being cyclic already makes it impossible to. So it being cyclic itself restricts the rotation. On this carbon over here, we have a double bonded oxygen. So there is only one thing on it. So this is we have this case over here. So there would be no geometric isomerism over this. There wouldn't be one over here. In this case, we have a double bond over here again, so no geometric isomerism there as well. We cannot have one over here since we have this. For a geometric isomerism in cyclic compound, we need something like this. So around this molecule over here, so around this carbon, we'll have this carbon with a CH3 and an H. We'll not consider the cyclic part of it. Oh, we also need something over here. On this side, we'll have C2H5. We could have a CH3 as well, that would work too. And a hydrogen, and then the cyclic part of it. We need 2 different molecules without the cyclic part of it for geometric isomerism in cyclic compounds. So this over here shows no geometric isomerism, so C is our answer. It will show optical isomerism only. Now we have to find which reagent gives a positive test result when added to carbon. We have a ketone group over here, so this is a ketone group, and we have carbon-carbon double bond. So a test for CC or C double bond O, so a ketone or a carbon-carbon double bond. So we need a reagent which reacts with them. Tollens reagent reacts with aldehydes, not with ketones, so this won't be a positive test result. Sodium carbonate does not react with ketone or carbon-carbon double bond, so that wouldn't be the answer. Iodine in the presence of alkali only works on methyl ketones. So CCH3 double bond O. This is the only type of ketone iron in present of alkali works with. We don't have that over here. We have 2,4-D in pH. This reacts with the ketone group. That's our answer. Now we have to state how many peaks would be expected in the carbon 13 NMR of carbon. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 carbon atoms over here. We have no symmetry in this, so none of the carbons are in the equivalent environments. So no carbon are equivalent to each other. So all of them will have a separate peak in the carbon 13 NMR. So A10 is our answer. Now in question 12, we are told from which two reactants could CH3C CH2CH2 COO CH24, so CH3 2CH2, so two of them. Then we have COO and then 4CH2, so CH2 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 1 2 3 4 and then a CH3. So this is an ester. It will be produced from the addition of a carboxylic acid and an alcohol. The carboxylic acid must be CH3 CH2 CH3 CH2 CH2 C double bond OH. This is 1 2 3 4. So this is butanoic acid. So A is our answer over here. And if we try to find out why it's butanol on the other end, this will be the part which has the OH. So we'll have OH CH2 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 CH3 1 2 3 4 1 2 3 4 5. So this is pentanol. So this must be pentanol with butanoic acid. The butanoic acid over here, the pentanol over here. So A is our only answer. Now in question 13, we are told that the reaction between ethanoic acid and lithium tetraaluminate hydridoaluminate 3 is best described as lithium tetrahydridoaluminate 3 is LiAlH4. Ethanoic acid is CH3COOH. LiAlH4 is used as a reducing agent in every case we study in A2. So this would be a reduction. The LiLH4 will reduce the primary alcohol into the carboxylic acid into a primary alcohol. So it will reduce this into CH3CH2OH. Now in question 14, we are told which substance will be least soluble in water. Sodium propanoate is a polar solute, so it will be the most soluble here. Propanoic acid will be slightly soluble since it's partially dissociated, and the hydrogen in the COOH can form hydrogen bonds with water. Same in the case of propanol, the OH group in the alcohol can form hydrogen bonds with water. Propanol will be our answer. In 15A, we are told that the mass spectrum of compound X shows a large peak at 59. This peak is due to fragmentation of molecular ion. We have to find which compound is most likely to be X. If we draw the compounds, 2-methylpropanol will be, so this is 2-methylpropanol. If we break this, this is 15 and this is 15 plus 15 plus 17 plus 12. This will form a peak at 59. If we look at pentane, CH3, CH. If we break this bond, we'll have 15 on this side and 14 plus 14 plus 14 plus 15 on the right. So 14 plus 14 plus 14. This has a peak of 57. So pentane is not our answer. Now for propanol, we have CH3, C double bond O, sorry, CH3, CH2, C double bond OH. If we break this, we'll get 15 plus 14 on this side, so 29, and 13 plus 16 on this side, so 29. If we break the bond over here, we'll have 15 on this side, and on the right we'll have 14 plus 13 plus 16, which is 43. This is 14, 13, 16. Propanol is not our answer as well. And for propanol, we have CH3, C double bond O, CH3. If we break the bond over here, we'll get 15 and 12 plus 15 plus 16, which is 43 again. 12, 15, 16. So A is our answer since it has a peak at 59. Now we are told that compound Y does not react with aqueous sodium dichromate and its infrared spectrum is given. If we use the data booklet, we can see that this has a peak for C double bond O. So it has one peak due to C double bond O. Since it has a peak for C double bond O, it will not be propanol or pentane since they don't have this bond over here. It can be propanol or propanol only. Now we are told that it also reacts with acidified aqueous sodium dichromate. The aldehyde propanol reacts with it. So propanol reacts with acidified aqueous sodium dichromate while propanol doesn't. So this must be propanol. And that's it for the MCQs. Moving on to section B. In question 16, we are given that a group of students investigated the kinetics of a clock reaction. Reaction 1 is given over here. Now we are told that a fixed volume of aqueous sodium thiosulfate and a small amount of starch was added to the reaction mixture. Now the added sodium thiosulfate reacted with the iodine produced in reaction 1 to carry out this reaction. Now we are told that when all of the sodium thiosulfate ions have reacted, the presence of iodine is detected by the formation of starch iodine complex. We have to state the final color in the first part. This will be blue, black or blue, the color of the starch compound when it reacts with iodine. Now in part 2, we're told in under appropriate conditions, the reciprocal of time can be used as an approximate measure of the initial rate. We have to explain why the concentration of sodium thiosulfate must be rho compared to the initial concentration of other reagents. So for the initial rate to be the reciprocal of time, so reciprocal of time means 1 by t. So for the rate to be equal to this, so for this the time has to be small. If the time is very big, it will not show the initial rate, it will show the average rate. So the sodium thiosulfate, all of the sodium thiosulfate must be used up in a small time, because if the time is bigger, the concentration of other stuff, so the concentration of H2O2, H plus and I minus, they will change. I2 won't change, so 2H plus and H2O2, so the concentration of H2O2 and 2H plus will change significantly if the amount of sodium thiosulfate used is large. So this is how we structure our answer. If the rate is affected by the other reagents, we cannot use this estimation over here. Now moving on to part B, we are given 4 reaction mixtures with different initial concentration of hydrogen peroxide, hydrogen ions and iodide ions. Each mixture had the same volume and contained the same amount of sodium thiosulfate and starch. Now we have to find the order of reaction with respect to hydrogen peroxide, hydrogen ions and iodide ions. Between mixture 1 and 2, the hydrogen peroxide concentration is halved. The other concentrations are kept the same, and the rate of the reaction also halves over here. So 5.13 by 2.56 is 2. So the reaction also halves. Or if we consider the flip side, if we go from reaction 2 to 1, if we double the concentration of hydrogen peroxide and keep everything else the same, the rate of reaction doubles. So order of reaction with respect to hydrogen peroxide will be 1. Now we have to consider in respect to hydrogen ions. This is the only place where we have a change in the concentration of hydrogen ions, but we also have a change in concentration of iodine over here, so we cannot find that out just yet. We have to know the order of the reaction with respect to iodine first. We can use mixture 2 and 3 to do that. There is a change in iodine ion concentration that doubles over here, and we can compare 1 and 3 instead. So the iodine concentration doubles, the other concentrations remain the same, and if that happens, the rate of reaction also doubles. So it's first order with respect to iodine ions. Now for the hydrogen ions, we can consider 1 and 4 directly as well without using other stuff. So in between 1 and 4, this remains the same, this remains the same. The change is only in the hydrogen ion concentration. The rate of reaction almost remains the same, so from this to this, the change into 0.955, so basically 1. So if we multiply, if we change this 10 times, so we're having 10 times more hydrogen ions over in 4, so 0 order because there is no change. Between mixtures 1 and 4. The concentration of H plus is increased by a factor of 10, and the rate is unchanged. So we have to write the overall rate equation for reaction 1 using our answers to part B1. So rate will be K times the concentration of hydrogen peroxide to the power 1 times the concentration of iodide ions to the power 1. Now we're told that all four mixtures contained 8.5 into 10 to the power minus 4 moles of sodium thiosulfate. We have to calculate the amount of iodine that had been reacted with the sodium thiosulfate when the color changed in reaction 2. If we go and look into the mole ratio, 2 moles of sodium thiosulfate reacts with 1 mole of iodine. So the amount of iodine reacted would be twice of half of this. So moles of iodine will be half into 8.50 into 10 to the power minus 5, which would be 4.25 into 10 to the power minus 5 moles. Now in part 4, we have to calculate the rate of reaction in mole per dm cube per second with respect to hydrogen peroxide using the answer from B3. The stoichiometry of reaction 1 and data from mixture 1. We are given the total volume of each mixture was 0.05 dm cube. Here the time taken was 195 seconds, so the rate of loss of iodine was equal to 4.25 into 10 to the power minus 5, which we found in the last part, divided by 195 seconds. So 2.18 into 10 to the power minus 7 mole per dm cube, mole per second. We don't have the dm cube yet. Now we use this to find it in mole per dm cube. So reaction rate would be this divided by the volume. So if we divide this with mole per dm cube, we get this unit over here. We can figure out what to do with the unit itself. So 2.18 into 10 to the power minus 7 divided by 0.050 dm cube, we'll get a value of 4.36 into 10 to the power minus 6 mole per dm cube per second. Now we have to calculate the value of the rate constant of reaction 1 using data from mixture 1 and our answer to B2 and B4. So K will be we have the rate equals to K times concentration of H2O2 times the concentration of I minus. So the K will be rate divided by the concentrations. The rate is 4.36 into 10 to the power minus 6 and the concentration is 5.4 into 10 to the power minus 2 and 8.2 into 10 to the power minus 3. If we figure this out, we'll get 9.84 into 10 to the power minus 3. The unit to find the unit, we have the rate, which is mole per dm cube per second. On the left we have the unit of K over here times the concentration is in mole per dm cube, and we have two of them, so mole square per dm to the power minus 6. If we want to find that, we have to do mole per dm cube per second divided by mole square dm to the power minus 6. We'll have mole to the power minus 1 dm to the power 3 second to the power minus 1. So that's our unit. So in this table we have the value of ln of the rate, the natural logarithm of the rate, and the temperature at which the reaction is taking place. Now in this information we are given this, that one of the students misread the thermometer in their experiment. So we'll have one anomaly in our graph. From that we can find out which student made the error, which value over here is wrong. Now we are told that using the Arrhenius equation we can find the activation energy by plotting a graph of the natural logarithm of the rate against 1 by temperature, reciprocal of the temperature, and the gradient of the resulting line of best fit can be used in the Arrhenius equation to determine the value of activation energy in kilojoule per mole. So our gradient would be minus activation energy by R, which is 8.31 into 8.31 joule per Kelvin per mole. Here we'll draw our graph. On the x-axis we'll have 1 by temperature. So this thing over here, the values range from 0.003 to 0.00360. So we can take 0.0031, so 0.0001 as the, so each gap can be taken as 0.0001. If we start from 0.003, we'll get 0.0031, 0.0032, 0.0033, 0.00. That's all we need, since 0.60 is our largest value. Now in the y-axis we have to place the natural log of the rate. Our values range from minus 1.8 to minus 6. So we can start from 0, then go minus 1, minus 2, minus 3, minus 4. This is ln rate, and this is 1 by T, and the unit for this is Kelvin to the power minus 1. If we plot our graph, the first set of values is minus 1.8, 0.003. So minus 1, this is minus 1.8. The next value is at minus 2.5, 0.0031. So over here. The next value is at minus 3.6, 0.00325. So 325 is over here, and minus 3.6. So minus 3.6 is over here. Minus 3.225 is over here. So this is where we'll have our point. The next set of values is minus 4 and 307. So minus 4 over here, and minus 4 and 0.00326. So minus 4 and 326 over here. The next pair of values is minus 4.7, 0.00343. 4.7, 343, 4.7 is over here. 343 is over here. And the last pair of values is minus 6, 0.00360. 360 is over here, and minus 6 over here. So this is, now if we look at this, this is our anomalous point. We'll ignore that and draw a line of best fit for the other ones. Something like that works. Now we'll find the gradient of this. Gradient is, so we'll consider this point and this point. This is minus 6.123, minus 6.3. This point is minus 1.5678, minus 1.8. This is 0.003, 1 minus 1.8, and this point is this value is 0.00363. 1, 2, 3. So that point is minus 0.00363, comma 6.3. If we calculate the gradient, it will be y2 minus y1, which is minus 6.3 minus 1.8, and x2 minus x1. So 0.00363. This won't be negative, and subtract that, 0.0030. This is our gradient over here. If we calculate this, we'll get a gradient of minus 7143. Now minus 7143, the gradient is equal to minus EA by R, activation energy, divided by 8.31. The minus cancel out. The activation energy will be 59,360 joule per mole. This will be positive, so if we convert it into kilojoule per mole, we'll get plus 59.4 kilojoule per mole. Now we are told that the students all use thermometers capable of reading the temperature to the same precision. So the error was made by minus 4.7, right? Oh, the error was made by minus 4. So This guy made the error. We are told that every thermometer is capable of reading to the same precision. So from the values of temperature we have, it seems like the thermometer can read to the nearest 0.5 Kelvin. His temperature reading was wrong, but his lawn rate reading was right. So the problem is in his x value. So the y value would be the same, but the x value would change. So for -4 is value of 1 by t must have been around 0.331. So 0.00331. So his temperature must have been, so 1 by t is 0.00331. So the value of t must have been 1 divided by that. So 1 divided by 0.00331, which would have been 302 Kelvin to the nearest 0.5 Kelvin. Now in question 17, we are given some values to be used in a Born-Haber cycle for MgCl2. We are given this Born-Haber cycle over here. So from MgCl2, A over here is the enthalpy change of atomization of magnesium. So the magnesium solid would become magnesium gas, the chlorine would remain the same. So we'll have magnesium gas plus Cl2. We are given this step over here as well. From this, the changes in the chlorine 2. So this is the enthalpy change of atomization of chlorine. Since 2 moles are formed, this will be 2 times D. So 2 into D. And here we have magnesium 2 plus, we have magnesium over here. So in this case, we'll have magnesium plus gas plus Cl2 gas plus 1 electron. This is the first ionization energy of magnesium, which is B. And then we have the second ionization of magnesium, which is C. Then we have twice the electron affinity, and this is the lattice energy. So when we go from magnesium 2 plus plus 2Cl minus to magnesium solids, this is the lattice energy, which is E. So if we have to calculate the value of the electron affinity of chlorine, now if we look at this, A, B, C, 2D, so everything except F is in clockwise direction while F is in anti-clockwise direction. So the summation of everything else will be equal to F. F is minus 641. This will be equal to the sum of everything else. So we have A plus B plus C. So 148 plus 738 plus 1451. So this is ABC. We have twice D, so 2 into 122 plus twice the electron affinity. So twice the electron affinity of chlorine, and we have E over here. The value of E is minus 2526. From this, if we calculate electron affinity of chlorine, we'll find this to be minus 348 kilojoule per mole. Now in part 3 we have to explain why when magnesium reacts with chlorine, MgCl2 is formed rather than MgCl3. Now if it's for MgCl3 to be formed, we also need the third ionization of magnesium. The magnesium has a structure, so 1s2, 2s2, 2p6, 3s2. So after we remove the first two from the 3s, we have to remove the next one from the 2p subshell. So we need a very high energy to remove one electron from the 2p subshell over here. And the lattice energy will not compensate for that. So MgCl, the lattice energy of magnesium MgCl3 will not be as negative to compensate for the highly positive third ionization energy of magnesium. So if there is a large arrow over here for the third ionization, but this arrow for E isn't as big, so it will be slightly longer. However, it won't compensate for this, so this minus this will be somewhere over here. So the Delitzsch formation for MgCl3 will be positive, might be positive. It will either be less negative or it might be positive. So if it's an endothermic reaction, it needs energy, so that's less stable than MgCl2. Now in part 4, we are given that the standard molar enthalpy change of solution of magnesium chloride is given in the table. We are given the Delitzsch hydration and of Mg2 plus and Cl minus. We have to calculate the standard molar enthalpy change. So molar enthalpy change of solution, we'd have to use a Hesse cycle over here. If we draw the Hesse cycle for this, we'll have Mg2 plus 2Cl minus gas. This will form Mg2Cl2 solid. So this is the lattice energy. Now the solution, Daylight solution will be the enthalpy change when we go from MgCl2 to solid to MgCl2 aqueous. So this is the Daylight solution. Now if we go from Mg2 plus and 2Cl minus gas to MgCl2 aqueous, we'll have the hydration enthalpy of magnesium plus the hydration enthalpy of chlorine times 2, since there are 2 moles of chlorine. So Daylight if we consider it clockwise, minus 2526, and Daylight solution are in clockwise, the rest two are in anti-clockwise. So minus 2526 plus Daylight solution equals to minus 1920 minus 364 times 2. So Daylight solution would be, if we calculate this, we'll get a value of minus 122 kilojoules per mole. Now we have our 6 marker over here. We're told that lattice energies from Born-Haber cycle are based on experimental values. Theoretical lattice energies can also be calculated. Experimental and theoretical values for 3 different crystal lattices are shown. So sodium fluoride, magnesium fluoride, and magnesium chloride. We're given the experimental and the theoretical lattice energies. We have to discuss the reasons for the differences in the 6 values in terms of the structure and bonding in these 3 substances. For the first pair of values, the theoretical and experimental values are almost the same. In the second pair of values, the experimental value is slightly more negative than the theoretical value. And in magnesium chloride, the experimental lattice energy is significantly higher than the theoretical one. We have to explain the differences in the differences. In the first 2 questions, between the first pair, the anion is the same while the cation is different. The magnesium ion is smaller than the sodium ion, so it has a greater polarizing power or greater charge density as well. So it has a higher polarizing power. So if we begin right there. This explains the difference in these values. So this explains why the lattice energy for magnesium fluoride is around minus 2900, while that of sodium fluoride is around minus 900. Now we'll describe the change in differences. So the differences between the experimental and Theoretical values for sodium fluoride is 6, while that for magnesium fluoride is 44, and this is 200. For that, we have to explain that the magnesium ion is more polarizing, has a higher polarizing power than the sodium one. We don't have to describe the difference between this because it's close, and it's due to the change in halogen. We can also write that down, but we don't need this over here. If we write that down, we can say that now we'll talk about the polarizing power and the change in the differences. So magnesium chloride has the biggest difference. Biggest difference. As magnesium chloride has the greatest degree of covalent character, this is the reason behind the difference. So this is our answer to the 6 marker. Now moving on to question 18. uh, in part A we have to write the reagents in step 1 and step 2. In step 1 we go from ethanol to CH3CHOHCN. So to make a nitrile from analdehyde we need to react with HCN and KCN. Now in step 2 we convert the nitrile into a carboxylic acid. To do that we need dilute hydrochloric acid and H2SO. We can use either one of them. So now we have to complete the mechanism for step 1. This carbon is electropositive. This double bond will break heteroradically. There's a lone pair over here in this carbon, and this will attack this carbon over here. We'll get H, C, H, H. This will react with the H. This lone pair will attack this, and this bond will break. After this we'll have our product. So CH3 C N H. Now we have to explain why 2-hydroxypropanoic acid produced is not optically active. So why is this? This is 2-hydroxypropanoic acid. We have to explain why this is not optically active. When it's formed, a racemic mixture will be formed because around the C double bond O, it would be planar. So the CN minus nucleophile. So in this case, the CN minus nucleophile can attack from this direction or this direction, any of them. So with equal probability, so a racemic mixture of both enantiomers will form. Now in part C1 we have to state the type of reaction in step 3. Here we go from a carboxylic acid to an ester, so this is an esterification. Now in C2 we are told that a small amount of polyameric compound is formed during step 3. We have to deduce the structure for the repeat unit of the polymer. So for this CH3CHOH COOH, this is a CH3 group over here, so we added CH3OH. We could draw this. This could react with other others, so this could react with other molecules of itself. We don't need that here. So it could react with other OH groups, so CH3OH. So this can react with 2-hydroxy propanoic acid to form other products as well. So for the other products, this for the polymeric compound CH3CH OH COOH could react with another molecule of itself, so OHCH CH3 COOH. This carboxylic acid could react with this alcohol group, so we'll have this hydrogen, so 2 hydrogen and 1 oxygen leaving, this joining together over here, making the so this is how it would repeat. So OH from this would go away, would have another OCH. This is the polymer we'll have, so the repeat units would be OCH CH3CO. This is the repeat unit. Now in part D, we are given that the high resolution proton NMR spectrum of methyl 2-hydroxypropanoate. So this compound over here gives 4 peak, J, K, L and M. L and M are singlets with relative intensity 1 and 3. We have to find where that's from. The singlets, if there is a hydrogen with an oxygen, so OH, this hydrogen will give a singlet peak, and singlets will also be produced by carbon whose neighboring carbon has no hydrogen on it. So this will produce a singlet since it's with an oxygen. This 3 hydrogen will also produce a singlet because the carbon is join with the oxygen which has no hydrogen on it. We are given L and M, we have to find J and K. So this we are given the ratio of peak L and M and their intensity. This will be peak L and this will be M, since there are 3 hydrogen in M and 1 in L. So this will keep our ratio of 1:3. Now we have to find the number of hydrogen atoms in peak J and peak K. Peak J has a ppm of 1.3. So this will be for peak J. There are 3 hydrogen atoms on it, and there is 1 hydrogen atom in the neighboring carbon, so it will be a doublet using the n+1 rule. And peak K will be for this hydrogen over here. There are 3 hydrogen on its neighboring atom, so there is 1 as such, and 3 hydrogen in the neighboring carbon, so 3 + 1 will be 4, so it will be a quadruplet or a quartet. And that's it for section B. Now moving on to section C, question 19. We have to find the value of Kc over here. In this case, Kc will be the concentration of CH3 CH2OH times the concentration of CH3 CH2 COOH divided by the concentration of CH3 CH2 COO CH2 CH3. Since all of them are liquids, they are not in aqueous solution. The concentration of water will also matter over here. If everything else was aqueous instead of liquid, the concentration of water would not be considered because it would be a solvent in that case. So Kc will be, we need to find the concentrations. Initially we had 0.1 mole of ethyl propanoid. This is ethyl propanoid. And 2 moles of water. So we can make an ice table from here. So CH3. So initially we had 1.1 mole of ethyl propanoid, 0.2 moles of water, and 0 for the rest. Now we are told in the following information that the equilibrium mixture contains 0.0440 mole of propanoic acid. So this was 0.0440. So the change was 0.0440 as well. So this is minus 0.0440, since the mole ratio is 1:1, minus 0.0440 here as well, 0.0440 here. If we fill up the table, we get 0.0560 over here and 0.1560 over here. So our Kc would be 0.0440 times 0.0440 divided by 0.0560 multiplied by 0.1560. The value of Kc would be 0.222. It wouldn't have any units since the right side and the left side have the same number of moles. Now in part 2 we are given that the standard enthalpy change of this reaction is close to but not exactly 0. We have to explain this statement considering the type and number of bonds being broken and made. Here we are reacting a mole of water to reverse esterification. The forward reaction is the reverse of an esterification. The backward reaction is esterification. The number of bonds being made and broken are of the same type and number. The number of OH bonds being broken and made are the same. The number of same type and number. Of bonds so logically the standard enthalpy change should have been 0, but we are told that it's close to but not exactly 0. This would be because the environment of the OH bonds in the left side and the right side is not the same. Due to the change in environment, there will be a slight change in the bond enthalpy even if they're the same bond. So the first part, this part describes why it's close to 0, almost close to 0, and then we describe why it's not exactly 0. Now in part 3 we have to deduce the effect of increasing the temperature on the total entropy change del S total and on the value of the equilibrium constant. We have to assume that del S system does not change with temperature. Since del S system does not change, the change in del S total will be due to del S surrounding. We know that del S surrounding is equal to minus del H by T. We are also told that del H is for this reaction is close to 0. Since del H is close to 0, del S surrounding and in turn del S total will not change by a lot. If the entropy change is almost the same, the equilibrium constant will also be the same because we can have this, we know this relationship between the change in entropy and the equilibrium constant, which is del S total equals to R ln K, where K is the equilibrium constant, as del S total is almost the same. Kc does not change. Now in part B we are given that we are told that propanoic acid is a weak acid. We have to describe the difference between a weak acid and a strong acid such as hydrochloric acid. The difference is strong acid is almost completely dissociated while weak acid is partially dissociated. So all of the hydrochloric acid will dissociate into H plus and Cl minus ions, while propanoic acid will not do the same, only partially. So this is C. This is propanoic acid. CH2COOH. Its dissociation goes like this, so it will form CH3CH2COO minus ions and H plus ions. However, all of it won't dissociate into H plus ions, only a small part of it, but in case of hydrochloric acid, almost all of it will break down into H plus and Cl minus ions. A weak acid is only partially dissociated. Now we have to calculate the pH of 0.5 mole per dm cube hydrochloric acid. Since hydrochloric acid is a strong acid, the concentration of H plus ions and the concentration of the hydrochloric acid would be almost the same. Log base 10.5. This will come out to be 0.301. Now we have to calculate the pH of 0.5 mole per dm cube of propanoic acid. Propanoic acid is a weak acid, so we have to use a different method for this, using the value of Ka. The Ka will be the square of the H plus concentration divided by the concentration of propanoic acid, H CH3CH2COOH. The value of Ka here is 1.30 into 10 to the power minus 5. The concentration of hydrogen atom is what we need to calculate, and the concentration of CH3CH2COOH is 0.5. Since this is a weak acid, the dissociation will be very small, so the concentration of propanoic acid we can consider it to be the same at initially and at equilibrium position. So the concentration of H plus ions here would be 2.5495 into 10 to the power minus 3 mole per dm cube. From here we can find the pH. pH would be minus log base 10 of 2.5495 into 10 to the power minus 3. This would come out to be 2.59. So for the same concentration of strong acid like hydrochloric acid at a pH of 0.3, while this has a pH of 2.59. Now in part C, we are told that the number of moles of propanoic acid may be determined by titration with aqueous sodium hydroxide. We have to calculate the pH at the point in the titration where half the acid has been neutralized. When half the acid has been neutralized, pH will be equal to pKa. This will basically be an acid buffer because we are inserting a strong alkali into a weak acid. And for buffers, at the half point, the pH is equal to the pKa. So pH in this case will be minus log of Ka, which is 1.3 into 10 to the power minus 5. So pH would be 4.89. Now in part 2 we have to sketch the titration curve showing the pH when 50 cm cube of 0.5 mole per dm cube sodium hydroxide is added to 25 cm cube propanoic acid. Since the mole ratio would be 1:1, we'll have a vertical section at 25 cm. Since the concentration is 0.5, our vertical section will be from 7 to 9 since we are adding strong alkali and weak acid. So 7 over here, 10 over here, 7 to 10 is our vertical section. Our initial pH is 2.59. So this is 3, this is 2.6. This at half neutralization happens at 12.5 cm cube, so somewhere on this vertical line, and at that point we have a concentration of 4.9, so somewhere over here. And then we'll this will be almost horizontal near the half neutralization point and then start going up again. We have to suggest a suitable indicator for this titration, and we have to justify our choice referring to the curve in C2. Since this is a weak acid strong base titration and the vertical section is from 7 to 10, we can use any of the pH indicators with a working range between this. So we can use phenolphthalein here. Since the pK indicator because the pH indicator range, so the indicator's pH range lies completely within. We could have also used bromothymol blue or phenol red in this case. The pH range is the pH range for an indicator is the pK of the indicator plus or minus 1. So the upper range is pK indicator plus 1 and the lower range is pK indicator minus 1. So it's somewhere over there. In the data booklet, the pH range is given as well. And that's it for this paper.